Hello, good morning everyone. I am John Cornelius M. Lasarte and I am your reporter for today. Our topic for today is the analysis of variance and with the subtopics of one-way and two-way ANOVA or the analysis of variance together with the SCEF and Target test. I hope you'll enjoy and listen well. Thank you. Now let us have the lesson objectives. First is to use the one-way ANOVA technique to determine if there is a significant difference among three or more means. Next is to determine which mean differ using SCEF or Turkey test if the null hypothesis is rejected in the ANOVA. And lastly, to use the two-way ANOVA technique to determine if there is a significant difference in the main effect or interaction. Before we start, let us have first a review. What is variance? The variance is the average of the squares of distance that each value is from the mean. What is the formula for variance? We have variance is equal to the summation of quantity x minus x bar squared all over n minus 1. The analysis of variance using the one-way ANOVA. The assumption for the f-test for comparing three or more means. The first is the population for which the samples were obtained must be normally or approximately normally distributed. Second is the sample must be independent of one another. And last, the variance of the population must be equal. These are the steps in finding the f-test value for analysis of variance one way. The first step is to find the mean and the variance for each sample. Some have the given data of the mean and the variance like what we are going to use later on. So you don't need to compute it anymore. But always remember the formula for finding the variance because some are only giving raw data. For step 2, we need to find the grand mean, which is equal to the summation of all the samples or over the total sample population. Next is the step 3, finding the between group variance, which is equal to the summation of n times mean minus grand mean squared all over k minus 1. And the step 4 is the finding the within group variance, which is equal to the summation of quantity n minus 1 times variance all over the summation of n minus 1. Finally, we have the step 5. The step 5 is to find the f-test value using the formula f is equal to the between group variance denoted by s squared sub b divided by the within group variance denoted by s squared sub w. The other things that we need to know are the degrees of freedom denoted as dfn is equal to the k minus 1 where k is the number of groups, and the degrees of freedom denominator, the dfn is the degrees of freedom numerator, and FD is degrees of freedom denominator, which is equal to the n minus k, where n is the sum of the sample size of the group. Now let us have an example. A researcher wishes to try 3 different techniques to lower the blood pressure of individuals diagnosed with high blood pressure. The subjects are randomly assigned the 3 groups. Of the first group takes medication, the second group exercises, and the third group follows a special diet. After 4 weeks, the reduction in each person's blood pressure is recorded at an alpha of 0.05, thus the claim that there is no difference among the means. The data are shown here. The medication, we have here 10, 12, 9, 15, 13, and there is a given the mean, which is 11.8, and the variance 5.7, and the exercise and the diet has also the given mean and variances, so we don't need to compute it anymore. Now let's proceed to the step 1. First things first is always to state the hypothesis and identify the claim. For our null hypothesis, we have that all the means are equal, which is our claim. And for the alternative hypothesis, we have at least one mean is different from others. Proceeding to step 2, we need to find the critical values. Since k is equal to 3 because it has 3 groups and n is equal to 15, or the 15 responses or sample size, the degrees of freedom numerator is equal to k minus 1. Substituting the value of k, we have 3 minus 1 is 2 for the degrees of freedom numerator, and to the degrees of freedom denominator, we have n minus k. 15 minus 3 is equal to 12 degrees of freedom denominator. We are going to use the table H that is found in Appendix C, and the critical value that we found at an alpha of 0.05 is 3.89. Proceeding to the next step, we need to compute the test value using procedure outlined here. The first thing is to find the mean and variance of each sample. Those are if the given are only the raw data. But now we have been provided by the variance and as well as the means. So we need to proceed now to the step B, which is to find the grand mean. The grand mean is denoted by x bar sub gm is the mean of all values in the samples. The grand mean is equal to the summation of x all over n. We need to add all the samples and divide it by the total number, and we got 116 over 15, which is equal to 7.73. Another method, if there is an equal number of samples for each group, all we need to do is to add the mean of the first, which is medication, mean of the exercise, and the mean of the diet. After we total it, we're going to divide it by 3, and we will also obtain the grand mean, which is 7.73. Next is we are now going to find the between group variance denoted by s squared sub b. Now here in the formula, summation of n, quantity x bar minus grand mean squared all over k minus 1. The numerator of this formula is what we call the sum of the square between groups, and the denominator is the degrees of freedom numerator. So in this example, as we substitute all the given data, we now have here the sum of the square between groups is the 160.13, and the degrees of freedom numerator is 2. And the resulting is the between group variance, which is also known as the mean square between groups. Proceeding to the next step is we now find the within group variance denoted by s squared sub w, and now it is equal to the summation of quantity n minus 1 times the variance all over the summation of quantity n minus 1. Now here in this formula, we have here the whole numerator is what we call the sum of the square within groups, while the denominator is the other form of the degrees of freedom denominator. So as we substitute our given values, we obtain the sum of the square within groups, which is 104.80, and the degrees of freedom denominator, which is 12, and the resulting quotient is what we call the within group variance, also known as the mean square within groups. Now let us proceed to the step E, which is to find the f-test value. We are going to get it using the formula f is equal to the between group variance divided by the within group variance. Substituting the value, we get 80.07 divided by 8.73. We get 9.17 as the f-test value. Then we make decision on the step 4, which is to reject the null hypothesis since the 19.7 is greater than the critical value 3.89. Finally, in the step 5, we're going to summarize the result, and there is enough evidence to reject the claim and conclude that at least one mean is different from the others. Now, for us to be able to easily visualize the result, we are going to plot it in the analysis of variance summary table. As you can see here, we have here the data that we have computed in the previous steps on the step C, D, and E, and we're going to plot it in the summary table with its corresponding designations. Based from this analysis table, we can now clearly see the process and how we get to the f-test value. Now we can see the sum of the squares between groups, which is 160.13, divided by the degrees of freedom numerator, which is 2. We got the mean square between groups, which is 80.07. On the other hand, the sum of the squares within group, which is 104.80, is divided by the degrees of freedom denominator, which is 12, and we get the mean square within groups, 8.73. And to be able to obtain the f-test value, we divide the mean square between groups, 80.07, to mean square within groups, 8.73, and we get the f-test value, which is equal to 9.17, which we use to compare to the critical value that we obtained in the earlier step, for us to be able to come up with our decision and conclusion. Now, there comes the time that when the null hypothesis is rejected, we sought to know where is the significant difference lies. Now, that is where the SCEF test is applied. Now we're moving on to the analysis of variance using the SCEF test. In the SCEF test, we use the formula quantity x bar sub I minus x bar sub j raised to 2 all over the within group variance times quantity 1 over n sub I plus 1 over n sub j, where x bar sub I and x bar sub j are the means of samples being compared, and n sub I and n sub j are the respective sample size, and s squared sub w is the within group variance. To find the critical value f, for the SCEF test, multiply the critical value for the f test by k minus 1. Then there is a significant difference between the two means being compared when f sub s is greater than the f. Now we have here the analysis of variance summary table that we obtained earlier from the example 1. This is the raw data and our summary table that we formulated earlier. We're going to apply the SCEF test on that example situation since we earlier rejected its null hypothesis. Now, for the solution, we substitute first the value of, we compare pairs, the first mean and the second mean. And for letter B, we compare the second mean to the third mean. And letter C, we compare the first mean to the last mean. By substituting its value to the given formulas, we obtained on the first comparison 18.33, second comparison 4.14, and the third comparison is 5.05. The critical value of f at an alpha of 0.05 with the degrees of freedom numerator 2 and degrees of freedom denominator 12 is we substitute the value k minus 1 times critical value, which is equal to 3 minus 1 times 3.89, which we get earlier using the H table. We obtain 7.78. Now, since the only f-test value for part A, which is the comparison of the first and the second mean, is greater than the critical value 7.78, the only significant difference is between the first and the second mean, that is, between medication and exercise. Now, another way or method that we can use in order to find where the significant difference lies is what we so-called the turkey test. In turkey test, turkey test is represented by Q, and we have the formula x bar sub I minus x bar sub j all over the square root of the within group variance divided by the n, where x bar sub I and x bar sub j are the means of the samples being compared, and then is the size of the samples, and s squared sub w is the within group variance. When the absolute value of Q is greater than the critical value of the turkey test, there is a significant difference between two means being compared. Now let us apply on the same data that we used on the first example regarding the medication, exercise, and diet. So for letter A, we compare the first and the second mean. For letter B, we compare the first and the third mean. And lastly, for letter C, we compare the second and the third mean. By substituting the values to the formula, we got, for letter A, the first comparison, we got 6.06. The second comparison, we got 3.18. And lastly, we got negative 2.88 for the last comparison. Now, to find the critical value for the turkey test, we are going to use table N in appendix C. The number of means k is found in the row at the top here, and the degrees of freedom are found in the left column denoted by B here. So since k is equal to 3 and degrees of freedom 12, an alpha of 0.05, the critical value that we obtained or we found is 3.77. Hence, the only Q value that is greater in absolute value than the critical value is the one for the difference between the first and the second mean. The conclusion then is that there is a significant difference in the means per medication and exercise. These results agree with the SCEF test analysis. Now, let's finally proceed to the analysis of variance using the two-way ANOVA. It is very different from what we have discussed earlier, which is the one-way ANOVA. In the two-way ANOVA, we are talking about the two independent variable or factor that we are going to test their effect on one dependent variable. In order to analyze its variance, we need to use the two-way analysis of variance, or ANOVA, because it is much complicated. Like for example, in this picture, does the type of soil in the food for plant, which is the two different independent variable, affects the height of the plant, which serve as the dependent variable. Now, let us deal with it. First, the assumption for the two-way ANOVA. The first is the population for which the samples were obtained must be normally or approximately normally distributed. The second is the sample must be independent Number 3 is the variances of the population from which the samples were selected must be equal. And lastly, the group must be equal in sample size. We need to know first the steps in the two-way ANOVA. And these are, first is to state the hypothesis, second is to find the critical value for each F-test, and then complete the summary table to get the test value, make a decision, finally summarize the results. Now we have here the ANOVA summary table. As you can see here, it is much complicated compared to the first summary table on the one-way ANOVA. Because here we have the first independent variable, and B represents the second independent variable. Then A times B represents the interaction between the two variables, and we also have the within error, and the rest follows the same format except for this, which is we are going to multiply the corresponding items for the first and the second independent variable to obtain this row. In the table, SS sub A represents for the sum of the squares for factor A, SS sub V is equal to sum of the squares for factor V, SS sub A times B is the sum of the square for the interaction of factor A and V, SSW is the sum of the squares for the error term within group. A is the number of levels for factor A, B is the number of levels for factor B, and N is the subjects in its group. Now we also have the formula MS sub A is equal to SS sub A over A minus 1, MS sub B is equal to SS sub B over B minus 1, MS sub A times B is equal to SS A times B all over A quantity A minus 1 times quantity B minus 1. And lastly, we have MS sub W is equal to SS sub W over AB times quantity N minus 1. Now we have the F value for the factor A, which is equal to the mean square for factor A divided by the mean square for the within group variance, with the degrees of freedom numerator equals to the A minus 1 and degrees of freedom denominator, which is equal to AB times quantity N minus 1. For the F value for the factor V, we have the mean square for the factor V divided by the mean square for the within group, with the degrees of freedom numerator equal to B minus 1 and degrees of freedom denominator, which is equal to AB times quantity N minus 1 also. For the F test value of the interaction between A and B, we have the mean square of the interaction A and B divided by the mean square of the within group, with the degrees of freedom numerator equal to the quantity A minus 1 times quantity B minus 1 and degrees of freedom denominator, which is also equal to A times B times quantity N minus 1. Now, to make it clear, let us first have an example. In this problem, a researcher wishes to see whether the type of gasoline used and the type of automobile driven have any effect on gasoline consumption. Two types of gasoline, which are regular and high octane, will be used, and two types of automobiles, which are two-wheel and the four-wheel drive, will be used in each group. There will be 2 automobiles in each group for a total of 8 automobiles used. Using a two-way analysis of variance, the researcher will perform the following steps. Now we have here the data in miles per gallon are shown in this table. the summary table is given. We can now see the type of automobile, two-wheel drive, four-wheel drive, the type of gas, which is regular, high octane with a corresponding scores of 26.7, 25.2, 32.3, 32.8, 28.6, 29.3, 26.1, 24.2. Another given is that ANOVA summary table which has already the sum of squares for the factor A, which is the gasoline, factor B, which is the automobile, and the interaction between the gasoline and automobile, and also the within group error, and its total. So these things are given. We are not going to compute for it anymore. We are going to proceed to the solution, starting with the step 1, which is always to state the hypothesis. And the hypothesis for the interaction are this. For this kind of analysis or ANOVA, we have 3 pairs of hypothesis, null and alternative hypothesis. For the first pair of null and alternative hypothesis, there is no interaction effect between the type of gasoline used and type of automobile a person drives and the gasoline consumption. The alternative hypothesis is there is an interaction effect between the type of gasoline used and the type of automobile a person drives on gasoline consumption. For the second pair of hypothesis, the hypothesis for the gasoline types are: the null hypothesis is there is no difference between the means of gasoline consumption for 2 types of gasoline, and the alternative hypothesis is that there is a difference between the means of gasoline consumption for 2 types of gasoline. And the last pair is that the hypothesis for the types of automobile driven are: for the null hypothesis, we have there is no difference between the means of gasoline consumption for 2-wheel drive and 4-wheel drive automobiles, and alternative hypothesis of there is a difference between the means of gasoline consumption for 2-wheel drive and 4-wheel drive automobiles. We're going now to proceed to the step 2, which is to find the critical values for each f-test. In this case, each independent variable or factor has 2 levels. Hence, it is a 2x2 ANOVA table used. The factor A is designated as the gasoline type, and it has 2 levels, regular and high octane. Therefore, A is equal to 2. For factor B is designated as the automobile type. It also has 2 levels. Therefore, B is equal to 2. The degrees of freedom of each factors are as follows. Now, for the factor A, we have the degrees of freedom numerator, which is equal to A minus 1. We have 2 levels, so we have 2 minus 1 is equal to 1. The same with the factor B, we also have 2 levels, so 2 minus 1 is 1, also for the degrees of freedom numerator. For the interaction A and B, we have the degrees of freedom numerator is equal to quantity A minus 1 times quantity B minus 1. Substituting the both levels of factor A and B, we have 2 minus 1 times 2 minus 1 equals 1 times 1 is equal to 1. For the within error, the degrees of freedom denominator is obtained using AB times quantity n minus 1. So A is equal to 2 times B, which is 2, times quantity 2 minus 1. 2 times 2 is 4, times 1 is equal to 4. That is the degrees of freedom denominator. The critical value for f sub A test is found using alpha of 0.05, degrees of freedom n, degrees of freedom numerator is equal to 1, and degrees of freedom denominator, which is equal to 4. In this case, the f sub A is equal to 7.71. The critical value for f sub B is also the same, together with the critical value of the interaction between A and B, because they both have the degrees of freedom numerator equal to 1 and the degrees of freedom denominator, which is equal to 4. But take note that that is not always equal. It's just this case they both fall and obtain the same degrees of freedom numerator and also the denominator. So for the step 3, we have to complete the ANOVA summary table to get the test values. The mean squares are computed first. So the mean squares of the first factor A is obtained using the sum of the squares of factor A divided by A minus 1. By substituting the value, we get 3.920. So next is the mean square for the factor B is obtained using the sum of the squares of factor B divided by B minus 1. Substituting the values, we obtain 9.68. And for the mean square of the interaction between A and B, we got the sum of the squares of the interaction A and B divided by the quantity A minus 1 times quantity B minus 1. Substituting the given values for this formula, we obtain 54.080. And lastly, the mean square for the within group, we obtained it using the sum of the squares within groups or error divided by AB times quantity n minus 1. Substituting the given values for this, we obtained 0.825. Now, the next thing we're going to compute is to find the f values. Then for the f value of the factor A, we obtained it using the mean square of A divided by the mean square of the within group. We obtained 4.752 with the degrees of freedom. A minus 1 is equal to 1 and the degrees of freedom denominator equal to 4. For the f value of the B, we have here the mean square, which is equal to 9.680 divided by the mean square within group, which is 0.825. Also, we obtain 11.733, which has also degrees of freedom equal to 1 numerator yun, and degrees of freedom denominator, which is equal to 4. And lastly, for the f value of the interaction between A and B, we got the mean square of interaction A and B divided by the mean square of the within group. Substituting the given value, we obtain 65.552 with also the degrees of freedom numerator equal to 1 and the degrees of freedom denominator equal to 4. Now let us plot it to the completed ANOVA summary table, and it is shown as follows. Just like what we had earlier, we can see this in this table very clearly and easily. How do we come up with this one? So we divide 3.920 with df, and we got that. Same with here and here and here. Now in the case of the finding the f value, we get the mean square divided by the mean square of the within error for each item. Like here, 3.920 divided by 0.825, we get 4.752. And for the automobile, which is the f value of 11.73, is obtained using 9.680 divided by 0.825, and the last is the interaction value is obtained by 54.080 divided by 0.825, we got 65.552. For the step 4, we are now going to make the decision. Since f sub v is equal to 11.733 and the interaction of A and B the F value of interaction A and B is equal to 65.552 are greater than the critical value 7.71, the null hypothesis concerning the type of automobile driven and the interaction effect should be rejected. Since the interaction effect is statistically significant, no decision should be made about the automobile type without further investigation. Now, to sum it up, since the null hypothesis for the interaction effect was rejected, it can be concluded that the combination of the type of gasoline and type of automobile does not affect gasoline consumption. In the preceding analysis, the effect of the type of gasoline used and the effect of the type of automobile driven are called the main effects. If there is no significant interaction effect, the main effect can be interpreted independently. However, if there is a significant interaction effect, the main effect must be interpreted cautiously. To interpret the results of a two-way analysis of variance, researchers suggest drawing a graph, plotting the means of each group, analyzing the graph, and interpreting the result. We need to find the means for each group or cell by adding the data values in each cell and dividing by n. Now, for this problem, the means for each cell are shown in the chart here. Plotting it to the graph, we obtain that when such an interaction occurs and the intersection is significant, the interaction is said to be this ordinal interaction. As we plot what is given here in the chart based on our previous problem or case, we got a disordinal interaction. And when there is an ordinal interaction, we could not interpret the main effect without considering the interaction effect. But this is not only the case. There is also two other cases, which is if the lines do not cross each other, nor are they parallel. If the f-test value for the interaction is significant and the lines does not cross each other, then the interaction is said to be an ordinal interaction. So as we can see here, the two lines did not intersect, so it means it is an ordinal interaction and the main effects can be interpreted independently for each other. And lastly, finally, when there is no significant interaction effect, the lines in the graph will be parallel or approximately parallel. When this situation occurs, the main effects can be interpreted independently of each other because there is no significant interaction. So, generalizing the concept of the analysis variance, commonly we use the variance to get the average of the squares of the distance that each value is from the mean. But when it comes to the test hypothesis concerning mean of 3 or more population, we use what we so-called one-way analysis of variance or one-way ANOVA. There comes the cases after performing ANOVA that the null hypothesis got rejected, and to be able to know where the significant difference between the mean lies, we use the SCEF test when the group is either have the same sample size or not. And another one is the turkey test, which is very ideal to use when the group have the same sample size. Now, when we are dealing with two independent variable or factor to test their effect on the dependent variable, the analysis of variance is quite complicated. That is not a time where we are going to use the two-way analysis of variance or two-way ANOVA. Well, that's all. Thank you for listening. I hope you enjoy and learn from my reporting. Thank you so much.